This video is going to focus on a tool called correlation, and to a lesser extent, it's going to focus on something called bivariate regression. We don't really care about bivariate regression very much. I'll point out the one utility it might have for us. We really do care about correlation for most practical analyses. But we need to understand bivariate regression enough to understand the one thing it might add, and because in the next video, when we go to multivariate tools, regression is the name of the game, and so we need to lay out some beginning understanding of what it is. So there have been a series of previous videos that have talked about important content that you need to know before you can work with the information in this video. The Framework for Applied Statistics video explains what I am doing and what I'm not doing, and how this is about preparing you to do practical statistical technician kind of work. It's not really not explaining the undergirding reasons why statistical analysis works the way it does. The introduction to JASP is necessary to understand the stats program that I'm using in these examples and in these videos, because it's a free open source program, so it avoids the problems that expensive paid versions of stats programs introduce for people who are trying to do it in limited budget practical settings. Nonetheless, JASP has some limitations, and that video talks about them a bit. There's a video on shape, strength, and significance. Those are necessary for all bivariate and multivariate analyses, but in particular, that video focuses on shape, strength, and significance, the way you would look at them for bivariate analyses, which is what we'll look at here. And then there's a video on central tendency and dispersion. The point here isn't so much that you need to understand how those tools work and that you'll use them here, but the understanding of basic dispersion and trend is necessary for a conceptual understanding of the tool we're going to use here. There are other videos in the series as well that talk about a variety of things that could help you to understand some of what's talked about here. The framework is basically built around three pieces: a very simplified choosing grid that's going to help you pick a statistical tool that's meant to get the job done for you, a list of things that we can do statistically, 4 different things, and saying which ones of them do we need to look at to be able to answer a question, depending on what tool we've used, particularly depending on whether we're doing 1 variable, 2 variable, or multivariate kind of analyses, and then 5 guidelines that will help us to think about how we might write up the results for any particular analysis we run and make sense of what it tells us. So the whole framework is meant to provide a practical grounding for doing immediate results. Our analysis question this go around is about the percent of the population saying prostitution is never justifiable around countries of the world. This is from the World Values Survey, and so there were only about 30 or 40 countries that were actually surveyed and that we have data for. But we want to find out for those countries if the percent of the population saying prostitution is never justifiable is related to unemployment rates, government spending, GDP per capita, or the Human Development Index values. Some of these we have worked with before, some of them we have not in previous videos. The data set I'm going to work with is the world data set I've put together from UN data, World Health Organization data, World Bank data, data from a variety of different think tanks, and so forth. The variables in particular that we're going to work with here are the variable about prostitution discussed in previous videos, a variable that basically measures unemployment rates across the countries, a variable that looks at government spending. It puts it into a particular 0 to 100 scale, so it isn't intuitive how the numbers work, but it's basically saying how much does a government spend relative to its production. And a GDP per capita variable. GDP is basically a count in monetary units, so in the US it would be dollars, of all of the goods and services that are consumed. So every time something is produced and sold, or a service is provided and purchased, then you count up the dollar amount of all that, and you can basically find out how much gross domestic product, how much is produced and consumed there is for every country. But because a 330 person country like the United States, roughly 330 million people, compared to a, say, 33 million country, would have a lot more produced and a lot more consumed just because there's 10 times more people, you can see that you're going to need to divide by the population size and get a per capita number to be able to compare countries to each other, thus GDP per capita. The Human Development Index, as was discussed in a previous video, is a composite measure that looks at education levels in the population of the country, income levels in the population of the country, and life expectancy for the population of the country to identify where countries have developed human potential more than in others. Okay, so We ask ourselves, when we look at these particular variables, and there are 5 variables: percent of the population saying prostitution is never justifiable, unemployment rates, government spending, GDP per capita, and HDI values. These 5 variables, does the way the research question is stated, does it indicate that we want to basically just run each of these independently and not relate them to each other? Well, that wouldn't be correct, because the research question specifically says, is the dependent variable related to this set of independent variables? So we definitely aren't doing one variable analyses. And the way it's stated, it says, is the percent of the population saying prostitution is never justifiable related to this, 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 or this? So it's basically asking for a series of bivariate analyses. Okay, so we're going to be in this row, so any tool we choose is going to be in this row. Then we say that dependent variable, percent of the population, that says prostitution is never justifiable, is it categorical or scaled? It is scaled, so we're going to end up in this column. We're still choosing the tool. We get down a little bit and we say, oh, we need to figure out if our independent variables are nominal and ordinal, or if our independent variables are interval and ratio. Are they categorical? Are they scaled? And in this circumstance, they're all scaled, and so we're going to find ourselves in this column, which is going to lead us to correlation as the tool that we're going to use. And again, when people say correlation, unless they say otherwise, they usually mean Pearson's R. That's the tool that is called correlation broadly. Anytime you're doing bivariate analysis to actually answer any meaningful questions, you probably need to look at shape, strength, and significance, all 3, to be able to answer a question in a way that practical decision making can be concluded. So we have 2 choices if we have scaled variables in a bivariate analysis. The one that we're going to focus on primarily is correlation, Pearson's R. Shape is going to be seen, as will be explained, from the direction of effect, the sign on R. Strength will be seen in the actual value or magnitude of R. R ranges from 0 to 1, and so a number nearer to 0 means that there's nothing happening here. There's no predictive utility. These 2 variables aren't related. A value of 1 means they are perfectly predictive. You're never going to see a value of 1 unless you've done something very wrong. And so we're going to basically talk about threshold numbers like we did in the shape, strength, significance video of 0.1, 0.2, 0.3, 0.5, those kinds of threshold numbers that people debate which numbers are the ones we most want to trust for identifying small or large, weak or strong relationships. And significance, as always, is from a p-value, as is discussed in the significance portion of the shape, strength, significance video. And this time we'll be looking at a p-value that comes with the R coefficient. The other choice is bivariate regression. Again, I'm really encouraging you to not go here, except for one very specific limited circumstance where you might go here. But understanding regression is valuable because multivariate regression becomes the name of the game when you move to multivariate tools. So shape is identified from a direction of effect, but it's a sign on a slope identified as b, lowercase b. Strength is from a tool called the multiple correlation coefficient, or capital R, and this one is squared. But we also do a correction on it, so it's the adjusted R squared. You may not care at all where it comes from, but it'll be labeled adjusted R squared. And significance will be a p-value associated with that slope of b for the bivariate circumstance. Again, we have some assumptions. Every tool is only appropriate, including mathematical tools, in a context where it was meant to work and where certain assumptions are met so that it works correctly. We are assuming there are no missing data, no non-valid categories, as has been discussed at length before. We're assuming that there are no serious outliers. In this video, I'm going to show you an example of how we might see a bivariate outlier and why that is different than talking about outliers the way we have prior to now. Linearity is assumed with both correlation and with regression, multivariate or bivariate regression. And so we are going to have to talk about what it means to say that we think the relationship is a straight line. And then these are parametric statistics, so they assume normality in the distribution of values of the dependent variable in the population, and they do assume equal variances in the distribution of values in the dependent variable within categories of the independent variable, all of which was talked about in prior videos as well. So let's talk about correlation and not talk about bivariate right now. And what I want to do is I want to go ahead and jump over to the analysis program and take a look at doing this specific kind of analysis. All right, this is our analysis program. It's already had the world data set opened. Let me clear away what's there and show you. No, let's just start over. So here's the world data set that we've been working with that's being shown in this is the world data set then that we've been working with up to this point, and what we're going to want to do is work with correlation. But you notice it doesn't say correlation across the top here. It says descriptives, t-tests, ANOVA, regression, frequencies, factor. All right, we've dealt with all of these actually up till now except this one. And this is where you find correlation because it is seen basically as a bivariate tool that's leading toward linear regression, the type we're going to talk about. Another name for what we're going to work with is called ordinary least squares, OLS, regression. There are other forms of regression. There's logistic regression. There's something called weighted least squares. There's two-stage least squares. There's just regression is a very robust and varied tool. We're going to be looking at the basic version of linear regression called OLS linear regression. But first, let's start with this correlation matrix. Now, what we want to do is we want to jump our way down to the dependent variable, which is 656, and notice that we have a dialog box that just says dump in all the variables you want right here. All right, so I'm going to put this wave 4 prostitution variable, that is percent of the population, that says that prostitution is never justifiable, and I'm going to drop it in here, and then I'm going to add some independent variables. Let me actually just right now add one independent variable. I'm just going to add that unemployment variable because I included it in this for just a very specific example of something. So here's the unemployment value. Now, what you're seeing here is you're seeing a Pearson correlation coefficient. Notice that there's something called Spearman's rho. I just reported Spearman correlation coefficient here. And there's Kendall's tau b, which we saw in the cross tabulations video. Now, these are both ordinal correlation coefficients. Pearson looks at interval and ratio data, and so when you have data that has more specificity, more precision in the measurement, has higher levels of measurement, Pearson is the tool that you want to turn to. Thus, this is the default correlation coefficient that people talk about. All right, so we have that. We also, our alternate hypothesis, that is, we're saying that we think they're correlated, which means that the null hypothesis is saying they're not correlated, as is the usual assumption of the null in the social sciences. We have some additional options here. The only thing we want to really point out is that it is reporting significance, which means it's giving p-values for us to identify significance from. If we instead said to flag significant correlations, then it would actually put asterisks out beside the R value that would indicate if something was significant. 1 asterisk would mean it was significant at the 0.05 level, 2 at the 0.01 level, 3 asterisks would mean it's significant at the 0.001 level. There are no asterisks on this result because, as you can see from the p-value of 0.697, this is not a statistically significant result. Do be aware that oftentimes when people report these things in public presentations or in public publications, they don't report the significance, they don't put the p-value on, they actually just put the flagged significance with asterisks. That's very, very common. Okay, so here we go. Let me also throw in a correlation matrix plot. This is actually called a scatterplot by everybody in the world except JASP. There's another thing that JASP does that's really disappointing in this one place. You see here that we have the Pearson's R that is going to relate unemployment as a variable across countries to views of prostitution as a variable across countries, but nowhere here does it tell you anything about the number of cases involved. It really would be helpful, and this is the one real criticism I have of JASP, that it doesn't report an n value anywhere in here, and I have no option of doing that. Because now I don't know how many cases there are, except when I look at the scatter plot, and I see that there are, I don't know, I didn't count them, maybe 35 cases involved here that answered the world values survey. And so, we have 100 cases that have been dropped out of the analysis from the data set. It would be really good to know that. You need to know what cases are involved so that you can report appropriately what cases are represented. Now, this is a really interesting result. Let me unpack this result a little bit more and discuss what this tells us. So first, as you look at this correlation listing, you notice that it has the prostitution variable as the first variable in the left labels, and it has the prostitution variable as the first variable listed across the top of the columns. And you can see where this variable intersects itself in the table. There are just flat lines. That's because this variable is a perfect predictor of itself. So if I know a country's value on this variable, it in fact will tell me how to predict the country's value on that variable. Knowing your weight means I could predict your weight. So this would always be a Pearson's R of 1 because you're correlating a variable with itself. And unemployment, likewise, if I tried to correlate it with itself, would give a value of 1 as well. So this program just gives us these flat lines saying these aren't relevant to our analyses. But that's fine. We only wanted to look at the relationship between these two variables. And so I have a Pearson's R value, and I have the P value that goes with it. And you'll recall that the direction of effect is from the sign. Negative would mean that there's a negative relationship. An increase in one variable means a decrease in the other. And positive would mean that they move in the same direction. This is all in the shape, strength, significance video. So this is a positive relationship. As countries have higher unemployment rates, those countries tend to have a higher percent of the population that say that prostitution is never justifiable. Okay, the strength is indicated by the size, 0.068, so we have a magnitude of R, or as we'll see in this consideration of this scatter plot in a moment, the tightness of cases around the best fitting line. But this is very small. It's very near 0. 0.07 is very near 0. And so we say that really there's no relationship between these two. And the statistical significance uses p-values the same way it always does. What's the probability that we could get this result from a real-world set of cases if, in fact, the null was true for the population? Well, it's 0.697 on a scale of 0 to 1. So it's very high probability we could have gotten these results with the null being true in the population. And so we can basically not reject the null. We only reject the null and say it's statistically significant if this number is below 0.05. So it's positive, but it's very, very, very weak, near 0, and it is not statistically significant. But there's something else interesting to notice here. We can do several things with the scatter plot. Notice that a scatter plot always puts the independent variable on the horizontal axis and always puts the dependent variable on the vertical axis. So here on the vertical axis, we have the percent of the population saying that prostitution is never justifiable. And across the bottom on the horizontal axis, we have the unemployment rate of the country ranging from 0% unemployed to a 25% unemployed is the scale that's been put onto the horizontal axis. Now, a couple of things to notice. Let's look at the outlier in a moment, but first let's notice that the slope of the line tells us direction of effect. In the same way that we can look at the positive or negative sign in front of Pearson's R, we can look at the line. Is it sloping up, which means a positive relationship as you go to the right, which is higher on the independent variable? Does the line go higher as well on the dependent variable? If it goes up on both, it's a positive relationship. It doesn't matter if it's a slight slope up or if it's a very steep slope up. It's just, is it sloping up or is it sloping down, which we'll see some examples of in just a moment. If it's sloping down, it means that as you move higher on the independent variable, that you then have, as you move to the right and you have higher values on the independent variable, the line goes down. It means you're going higher on one and you're going lower on the other. It's an inverse or negative relationship. So the slope of this line shows me that there is, in fact, a positive relationship. The strength is graphically represented by how close these dots are. Each dot represents a case. So this dot is a country, and this country has an unemployment rate of roughly 15%. I mean, we'd have to get the exact value, but you can see it lines up right about above 15% unemployment. And it has a percent of the population saying that prostitution is never justifiable, very high, 99%. So this country, whatever country it is, was plotted here because it has a 15% unemployment rate. Sorry, didn't mean to press that. It has a 15% unemployment rate, and it has a nearly 100% of the population sampled saying that prostitution is never justifiable. Every one of these dots represents a country that is plotted where its value is for the independent and dependent variable. Now, if our prediction line, and that's what this straight line is supposed to be. It's supposed to be a prediction line. If our prediction line works well, all of the dots will be very close to that line. So what will happen is that the distance from each dot to the line will be very small. You can see that some of these dots are a very long way from the line. The way it's supposed to work, this is a prediction line. So if I came out here to 15% unemployment and I said, according to my mathematics, my best fitting line as my predictor, and that's what correlation and regression are doing, if I have a country that has 15% unemployment, what should I expect to see in terms of the percent of the population saying prostitution is never justifiable? Well, what I should expect to see at 15%, if I just go straight up, I hit the line, and where that line goes back over, I would say, well, I'd expect about 70% of the population to say that prostitution is never justifiable. For a country here on the independent value, independent variable, I would predict based on this best fitting line where they would be on the dependent variable. But you can see I'm way off. In fact, it's not 70%, it's about 99% for this case that has 15% unemployment. So I've had a lot of error in my prediction. And the goal of strength is always, one way or another, the mathematics differ from tool to tool, but it's about saying how well does knowing the independent variable help me to predict values on the dependent variable. Not all of these tools mathematically actually do a prediction, but in essence they are all logical ways of inferring a prediction. So in this circumstance, you can see that there's a lot of distance between the line and these dots. Now, if you're familiar with the statistical mathematics underlying a lot of statistics, or if you just know something like how a standard deviation is calculated, you may be familiar with the idea of the sum of squared deviations. What happens is they just take the deviations from the prediction line. That is, they take the deviation from what the line predicts will be the value on the dependent variable, and that's basically the straight up and down distance to the line, and they square those and add them up. Now, if it came to 0, it would mean that every case was right on the line. It would be perfect prediction, and so it would have a Pearson's R value of 1. But in this circumstance, some of them have very close to the line's placement, and so their distance to the line is 0 or just very small numbers, and they don't add up to much. But some of them have big distances, and so you end up with a lot of deviation from what the line predicts, and so you end up with a very small value. The closer the dots are to the line, if they're clustered right on the line, this will become a bigger Pearson's R, and if they're spread out far away from the line, this will be a smaller value. So here we have a positive relationship shown in the graphic, and we have a very weak relationship because the dots are spread very far around the line. Now, let's look at this outlier. Up till now, we've talked about outliers as being cases that have values that are far out away from all the other case values on a particular variable. But if you look at the values that are possible on the dependent variable, the percent of the population that says the prostitution is never justifiable, you can see that this is right in keeping. Just imagine that we lined them all up on just this value, just on this variable. Then we would find out this was right in the mix. It's not an outlier at all in values in the dependent variable. Similarly, if you took all of the cases and you just lined them up along their values on the independent variable, you would find that all of the cases pile up. And this one, it's a little bit above, but it's not very far. We probably wouldn't say it was an outlier here either. If we calculated a mean on this independent variable and then we took away the outlier and recalculated the mean, we'd probably find it made very little difference. It's not really much of an outlier on the independent variable either. And yet, it is clearly an outlier in this bivariate scatter plot. So when we scatter plot two variable patterns against each other, and now we have a bivariate pattern, you can see that now we have a bivariate outlier. It's not an outlier on the dependent variable, it's not really an outlier on the independent variable, but it is very much an outlier in the bivariate pattern. And what happens is, since this line is drawn in the place where we're trying to have the smallest sum of distances, this distance right here, the line is coming way down here to try to get, because if the line went, imagine this dot's not here, if the line went across all of these cases, it would basically not be very far from any of these lines, any of these dots. So we would sum up the variation. It wouldn't be far if the line went like that. But the distance for this one, if the line went like this, imagine the distance from this case to the line, that line would extend way up here, and the distance would be huge. And then because we use a sum of squared deviations, we would square that. And squaring a big number makes it really huge. And so now we've got this massive distortion. So the line, the best fitting line, by definition, mathematically means the line that has the smallest sum of deviations away from the line. Okay, so to get this into the keeping of the rest, it basically pulled the line way over. This line would go this way, and now it's been torqued way over to a nearly flat line because of this one bivariate outlier. Now, what am I going to do? Well, I only have two choices. Really, the first thing I would do is I would have to run this analysis like I just have, and I find out that Pearson's R is very weak, and it's positive, and it's not significant. And then I would find out what country that is. I'd have to go into the data, and I'd have to figure out what country it is. And then I would remove that country from this analysis. In JASP, that would probably mean that I would have to go in and delete, just give it a zero value, a blank value, not the number zero, but just give it a blank value, make it totally missing on one of the two variables so that it's dropped out of this analysis entirely. Then I would rerun this and I would see what my new results were. And if they were very different, then I would say, that outlier matters and I need to make it go away. All right, so that would be the way that we should handle this. But I only put unemployment in here because I wanted you to see an outlier. I don't really care about it as a predictor for the dependent variable at all. I wanted you to see how an outlier can be spotted in a scatter plot. Okay, another thing that we're going to talk about in just a little bit that the scatter plot can do for you in particular is, remember, we're assuming a straight line relationship. We're assuming a straight line can describe how values on the independent variable are related to the dependent variable. But sometimes there are results that are curved. And this straight line approach of correlation and bivariate regression doesn't see what's really happening with a curve. So we're going to look at an example of that in a moment. But right now I've shown you what happens with the unemployment value. Let me just go back here and say, unemployment, what a bother. Since we're not really running real analysis, I don't care. Let's just make it go away and use some other variables for our example right now. So I'm going to add the other variables that I had in my list earlier. So I'm going to put that government spending variable in, and I'm going to put the GDP per capita variable in. And then I'm going to put the HDI value variable in. Okay, so now what has happened in the program is I now have the correlation matrix that has a whole bunch of correlations between a bunch of pairs of variables. We'll look at that in a bigger picture in just a moment. And now I also have scatter plots for the relationships of the prostitution variable here with government spending, the prostitution variable with GDP per capita, and the prostitution variable with HDI values. But I also have the ways that each of these independent variables correlate with each other in Scatterplot. Now notice, see how the World Value Survey, how there are so few cases compared to the rest of these? Because the World Value Survey was only given in a few countries, relatively speaking. Look at this result. This result between the GDP per capita and the Human Development Index. Now there's a reason why I've put this particular pair, there are two reasons why I've put this particular pair of variables into my list of independent variables for you to see. One of those I can tell you now, and that's this curve, and the other one, the other reason why I've put this pair in there, I will explain in the next video, which looks at multivariate regression, because we're going to find out there's something very problematic about these two variables both being in the same analysis. But that's for the next variable. For right now, look at that curve. If you really were trying to draw a line that was as close as possible to all of the dots you could, you would draw a line that would be a big parabola. It would basically look just like this. But instead we have a straight line. And while this straight line does a pretty good job of being near the vast majority of cases, and so it works out okay, If a lot more of these cases had been piled up here, if it had really been much more, a much clearer parabola, then we basically would have had a line that would have been placed in a way that missed a lot of what's going on. If there's a curved relationship like this, and they don't happen often in life, but they happen sometimes, if you run a scatter plot, you can see if there's a curve. And if there's a clear curved pattern, even here you might say, well, there seems to be a bit of a curve here. To the extent that you say there's seriously a very obvious curve, then you violated the assumption of linearity, and you might want to be really careful about using correlation. I don't think there's enough curve here, I care. I don't think there's any curve here, I don't care. None of these are, but this one, there's enough of a curve. As it turns out, the curve is very slight, and almost all of the cases are very near the line. I'd say with this one as well, it's okay. But you can now imagine how a curve could create a real difficulty for a statistical tool that assumes linearity. We'll come back to this pairing of independent variables, HDI values and GDP per capita, in the next video when we're going to find out that there's another big problem they introduce for multivariate regression. But for now, let's go back and look at the results from this correlation matrix, as it's called, where it puts a whole bunch of bivariate analyses results into one table. There's no statistical control anywhere in this table. Everything you see is a representation of a bivariate relationship. They've just had a whole bunch of bivariate relationships reported in one table. And then we're going to look at these scatter plots and figure out what we learned from these things. Okay. So first, here's that correlation matrix. Because we said what we want to know is how each of these independent variables, government spending, GDP per capita in purchasing parity power dollars, and HDI in the 2018 report, how they relate to percent of the population that says prostitution is never justifiable. All the research question asked for is how each one of these related to prostitution view. All we care about are these three sets of results. We don't really care about how government spending relates to GDP per capita or HDI value. We don't really care about how GDP per capita relates to HDI in 2018. Although when we go to multivariate, we will look at this. It does matter what these numbers are as part of the assumption tests. But right now, we're just doing bivariate correlation. And so we're just going to look here and we're going to say, how do we understand what this tells us? Well, you recall that what we wanted to look at here was we wanted to look at the sign as the direction of effect. This is a positive relationship. As government spending is higher in a country, the percent of the population saying prostitution is never justifiable is also higher. It's positive. This is GDP per capita. As GDP per capita is higher in countries, the percent saying prostitution is never justifiable is lower. It's a negative relationship. As this goes up, the other goes down. This was positive. As this goes up, this also goes up. Here's a negative relationship. So as HDI value goes up, prostitution, the percent of the population with a negative view of prostitution, goes down. This is very strong. On that 0 to 1 scale, we could have a kind of 0.1 is very weak, 0.2 is weak, 0.3 is moderate, 0.5 is strong. This is strong. This is strong. And this is strong. Now, don't misunderstand. I chose these independent variables to demonstrate particular things. Like I chose the unemployment one specifically to show an outlier. And I chose HDI and GDP together because I need to show you something in the next video, and I needed two variables that matched up a certain way. I could have put a lot of variables in this analysis that had very small effects, like the unemployment number, even without an outlier. Small, weak effects in positive and negative directions, and that were not statistically significant. So this is not meant to say it's normal to see this happen. I just chose variables that provided us with this kind of an example. So if you're running bivariate correlation, then all you care about is if you put the dependent variable first in your list, it'll be right here, and you can just read down this one column and find out that this one is strong, positive, and significant, strong negative effect and significant, strong negative effect and significant. Now we could look at this as well in the scatter plots. So here we have a slope that shows that as you have greater amounts of the independent variable, it goes up. As you go to the right and have greater amounts of the independent variable, the line goes up, which means that you're now getting higher amounts on the dependent variable. So it's a positive relationship. More of this leads to more of this. positive relationship. Here we have a negative relationship. As you have a larger amount of GDP per capita, as you go to the right, the line drops down. And so you're going from higher values on percent of the population who say prostitution is never justifiable, you're going to lower. So as you go up on one variable, the line says as you move to the right and you're going up on the independent variable, you're actually going down on the dependent variable, a negative relationship. So you see the slope, positive, negative, negative. You just have to get used to, does the line go up or does the line go down? This is a positive relationship, this is negative, this is negative. These dots are all relatively tight around the line. You'd have to just go play around in JASP with a whole bunch of data, and you could look at some different examples, and you would see what it looks like to have dots that are scattered across the whole scale, and then you would have R values near 0. These also are all gathered relatively near the line, and these also are all gathered relatively near the line, which you already knew because we already said that all of these were strong relationships. Okay, so that's correlation. It's basically pretty simple. You need to look at the scatter plots to figure out if you have outliers, bivariate outliers. You need to look at the scatter plots to see if you have a big curve, which you should be worried about if you have a big curve. If we had data right here that kind of did this, where it went up really steep and then the cloud of dots turned and created this plateau effect, then the line would look very similar to this, but in fact it would be showing a very weak relationship because the dots weren't close. But that's curvilinear. All right, and you need to look at this correlation listing to find out direction of effect and strength and significance, direction of effect and strength and significance, direction of effect and strength and significance. So how would we report these results? Remember, we have these 5 guidelines. You're supposed to stay true to the cases, so you're going to try to say what cases are involved. We've already pointed out that the World Values Survey means that there aren't a lot of cases in this. It's not representative of all the countries of the world. You're going to try to be true to what the measures are, so you're going to want to make sure you explain what each of these variables are and how they're measured to the extent that your audience needs to know to be sure they're not misunderstanding what's being measured. And then you're going to try to describe the shape in words and with numbers, the strength in words and with numbers, and the significance in words and with numbers. So I would end up saying that as government spending increases across countries, the percent of the population that says prostitution is never justifiable increases as well. It's positive. In words, as this increases, and use the names of the variables. Don't use these cryptic names. Use real words so that your audience understands. So you'd say, as countries have higher government spending, they tend to have a higher proportion of the population that says prostitution is never justifiable. You hear, that's in regular words anybody can understand. Not as V101 gov spending increases V656 Prosta 4, right? Don't use these cryptic terms unless you're just talking to other researchers who are all familiar with them. So in words, that was the direction of effect. It's a positive effect. In strength, I would say this is a strong effect. Good enough. It's a big effect. Good enough. You're just using an adjective for strength. Strong, weak, big, small, moderate. Just pick an adjective and get it into your sentence somewhere. And then you report R. R equals positive 0.612. And now I have in numbers evidenced both my statement in words for the relationship of the direction of effect, and I have given an example in numbers of the magnitude or the strength. So I could say, as government spending increases for countries, they tend to have a higher percent of the population that say prostitution is never justifiable. This is a strong effect. And then in parentheses, R equals 0.612. I have now done strength and shape in words and in numbers. This is statistically significant. In parentheses, P is less than 0.001. Or you could say P is less than 0.05 if you're just staying with that common standard. I would do the same thing here. As GDP per capita increases for countries, the percent of the population that says prostitution is never justifiable decreases. This is also a strong effect. In parentheses, R equals negative 0.629, close parenthesis. This is also statistically significant. In parentheses, P is less than 0.001, close parenthesis. You get the idea. It's very straightforward to report the results here. All you have to do is write out the results of the direction of effect in words and then say use an adjective for the strength, and then say it is significant or it is not significant, and then report R and report P. That's pretty much all it takes to fulfill that. And then if you want to interpret what this might mean, well, you know what this tells us. It tells us this is what's happening, or this is why it's happening, or this is what people believe. That kind of interpretation would be something that you would do in separate paragraphs so that people don't get confused about what is the empirically verifiable claims that you've made and what are the interpretations and speculations you're making. People want that speculation. They will ask for it. They'll be like, well, you know this better than we do. You know at least some facts. What would you logically infer must also be true? That's all fine. Just make sure that people don't get confused about where you're connecting the empirical facts to the interpretations and speculations that you'd be making. All right. So here are those scatter plots. Now, we also said that you could do bivariate regression. And I'm going to say that there's only one thing. We're going to look at this really quickly in JASP, but there's only one thing we really care about in terms of bivariate regression. And I'll add that in quickly as an example. And then we'll save all of the discussion about regression for the multivariate regression video coming up next. Okay, so if I jump over here, and let me go ahead and clear this back out again. If I go over here and we look at these results and we go to regression. Okay, so now in linear regression, what I want to do is, again, I want to grab my dependent variable, which is 656. Okay, so prostitution wave 4. And now this is different. You remember that in the bivariate correlation box, I just piled in all the variables I wanted. Let's go back up to this. And you could see that every one of these is a bivariate result. Here's the correlation between the prostitution view variable and government spending. Here is a bivariate result between the prostitution view and per capita GDP. These are all bivariate results. There's no statistical controls being put into place here. And in this, everything was just listed in one box. By default, correlation is used as a bivariate tool. It is possible to do a multivariate correlation. It's called partial correlation. But this program doesn't even include it. Okay. On the other hand, regression is by default almost always used for multivariate work. So we're going to do a bivariate piece here, but it's only as an example. Really, this is a multivariate tool. You see, here we have one dependent variable off by itself, and then we're going to have the covariates. Covariates is just a way of saying list all of the independent variables you want to put into the model that are interval or ratio. All of the independent variables that are scaled. If you had a box that said, and you wouldn't in regression because it only works with scaled variables, but if you had a box that said fixed factors or something like that instead of covariates, it would be saying give me categorical data. You may recall seeing that in the ANOVA examples for comparison of means. Now, it is possible with linear regression, it is possible to mix scaled variables and categorical variables. It's just not easy. Categorical variables have to go through a process called dummy variables, and that's beyond the scope of what we're going to talk about. But be aware that if you ever do find yourself in a multivariate setting, well beyond the scope of this particular video, a multivariate setting with a dependent variable, and then you want to have interval ratio variables, and you want to have some kind of categorical variables loaded into the list of independent variables together, this is where you do it, but you have to do some manipulation of those categorical variables. All right. Right now, though, we just want to do a simple bivariate result. So let's just grab the government spending variable, and let's get it in here as an independent variable. If I put it in here, what you see is you see a whole bunch of things. So we're going to have to unpack what all of these are in a second. But notice in this list right here, there is one variable shown. But if I add additional variables beyond my government spending variable, so let's say I go ahead and add that 118, and I go ahead and add that 124 for HDI values. Now, what we have here is we have a listing of all the independent variables all being loaded together, but this is not bivariate. This is a multivariate analysis where we're getting results about how these things matter after controlling for each other. Oh my, that's not what we want right now. That's something for the next video. I hearken to it now only because you might be tempted, after I just showed you correlation, to just dump all the variables in this box. But don't do that. This is not a bivariate tool. So here is a bivariate result with our one dependent variable and our one independent variable. Okay, and what I'm going to do is just work with that one example to highlight a few specific things, and then we can set the rest of it aside until we do multivariate. So there are only a few places in these results that people will tend to look. So one is they will look up here at, this is the multiple correlation coefficient, capital R. We don't know what it is yet, but it's multivariate. Multiple correlation. It's a multivariate tool. This is a multivariate tool that we could use. This is a multivariate tool that we could use. So we'll look at this in the next video. This is an F-test, just like we did in the other ANOVAs. This is also an ANOVA, but instead of between group and within group sums of squares, now we have the regression results and the leftover, the residual, the error, the distance between the line and the plotted dots, right? And we're comparing those two, and then we get a ratio, and we end up with a probability value. This p-value goes with this multivariate correlation coefficient. That's all multivariate. Down here, we have particular results for each independent variable, and we have p-values for each independent variable. The intercept is something beyond our specific discussion here, but it just basically means unexplained variation. What we really care about in the bivariate setting is we care about this. For government spending, there is a slope, the slope of this line, such that this is by definition. For a 1 unit increase in the independent variable, which is government spending, for a 1 unit increase in this variable, whatever it's measuring, there will be a 0.5 unit increase in the dependent variable. Because it's positive, we know that a 1 unit increase here leads to a positive change of 0.5 in the dependent variable. So 1 unit more here, increase of this much in the dependent variable. If this was negative, we would say a 1 unit change here leads to a this much decrease in the dependent variable. And then we can see if that is statistically significant. So we get a direction of effect, plus or minus, just like with R. It's the same scatter plot. So this one's positive. It's a positive relationship. But now, instead of having a measure of effect size that has some sort of inherent clarity, we have, for a 1 unit change here, what's going to happen on the other axis. That's the one thing this adds. It's not an effect size, it's a prediction. So while it is in the realm of effect sizes, it's that kind of a tool. What you're really finding out is if you built a regression equation and you said, we're going to look at how many dollars was spent on each person who came to our agency, and then we're going to see what kind of outcome they had. And then we could basically run a regression. We could see, as dollars increased, what happened to their outcome value. Did it go up? Did it go down? How spread out are they? How much of these things? Maybe we'll find out that dollars spent has no relation, a very small R value, right? Which would mean, okay, so let's not go into interpretations there. Okay, so in this example, we would say for every dollar we add, how much change is there in the outcome score? That's what this unstandardized slope tells us. And then we could find out if that's a significant change. That's all we get from bivariate regression. You ignore everything else in bivariate regression. With multivariate regression, we care about this, we care about this. In fact, we're going to put a new box over here over the standardized slopes, and we're going to ignore the unstandardized slopes. But for right now, this is the one thing that you gain, and this is the one purpose for a prediction line in regression. Now, there's one other thing I want to mention. You notice that the multiple correlation coefficient, capital R, is squared. And you may recall there's something called eta that we squared. Back in ANOVA, in comparison of means, there was a discussion about eta squared. And we interpreted eta squared as the proportion of variation in the dependent variable that is explained or predicted by the independent variable. And this does a very similar thing. We'll talk about it next video, but this does a very similar kind of thing in a multivariate way. What we should recognize then is that if we go back to the correlation results, this is a circumstance where we could square this. Now, not all measures of association allow you to do this. Not all measures of correlation allow you to do this. So you can't just take anything. We talked about Kramer's V in an earlier video. You can't square V and read it this way. But you can square eta and read it that way. And you can square R. When you square Pearson's R, it gets its own special name. It's called the coefficient of determination. And so basically, if you took 0.612, and I'm doing it on a calculator, times 0.612, you would get 0.37. Now, what that tells us is that we can explain 37% of the variation in the percent of the population who says prostitution is never justifiable from government spending. It's a bivariate result, but we can square it. 0.612 squared becomes 0.3745. So 37% of the variation in the dependent variable is explained by the government spending independent variable. Similarly, we could take that point, I'm just going to call it 0.63, and we could square it, and we have 39%. So 39% of the variation in the dependent variable is explained by the GDP independent variable. Oh, and 0.7, well, 0.7, it's 49. I mean, we can do this in our head. 0.7 times 0.7 is 49%. So we would say, well, we explained 37%, and then we explained 39%, and then we explained 49%. And if you're paying attention, first, we now have a tool you might like. If you liked working with eta squared, if you liked that idea of talking about the percent of variation that is explained by the pattern in the independent variable, if you liked being able to say that, explaining percent of variation in the dependent by recourse to the values on the independent, then you should square R and report it that way. It's not done that way normally. Okay, by custom, R is reported unsquared. And by custom, eta is reported squared. This is because when you calculate eta in the mathematics, you actually end up calculating eta squared, and then you have to take a square root to get eta. Whereas in the mathematics that lead to the construction of R, you end up with R, and then you have to square it to get R squared. So they basically just said as soon as they got to something they could use, you're working this way and you get to eta squared, good enough. You're working this way and you get to R, good enough. And they didn't bother to make them both reported the same way. So if it seems a little odd that one is reported squared and one is reported not squared, eta is reported squared as the proportion of variation in the dependent variable explained by the independent, and R is reported not squared by threshold kind of considerations. So this is strong, this is weak. If that seems odd to you, it is. But you can do it either way with R if you wish to. But here's the other thing. So we had 37% explained, and 39%, and 49%. To most of us who can add, we're a long ways past 100% of the variation explained, which should worry us, because there's only 100% of the variation in the dependent variable. Cases only varied as much as they really did. What it's telling us is that these independent variables are related to each other. And so we need to control for the others to get net effects. That's the intention of why we use multivariate tools. So in the next video, we're going to go ahead and do exactly that. We're going to go ahead and make sure I didn't miss anything. Okay, we're good. We're going to go ahead and we're going to do the multivariate so that we can find out how much each of these independent variables actually predict the variation in the dependent variable, having controlled for the overlap in how they affect each other. All right. Correlation coefficients. They're simple, they're straightforward, they're easy to write up, don't overcomplicate it, and they're a very robust tool. We'll talk more about multivariate tools with multivariate regression in the next video.